To calculate the wattage of a three-phase heater bank, we will use a specific formula. The formula is wattage equals 1.732 times voltage line to line times line current times power factor. There are several steps required to calculate the wattage. Firstly, we must calculate the line current. The formula for line current is line current equals voltage line to line divided by resistance times the square root of 3. Based on the provided information, the line current is calculated as 240 volts divided by 24 ohms times the square root of 3, which equals approximately 4.62 amps. Secondly, we need to determine the power factor. For resistive loads like heaters, the power factor is typically assumed to be 1, also known as unity power factor. Thirdly, we calculate the wattage using the initial formula. The wattage is equal to 1.732 times the voltage line to line, which is 240 volts, times the line current, which is 4.62 amps, times the power factor, which is 1. The result is approximately 2560 watts. Therefore, the total wattage of the three-phase heater bank is approximately 2560 watts. It is important to note that this formula assumes the heater bank is a balanced three-phase load, meaning the three phases have equal currents. The line-to-line voltage refers to the voltage measured between any two phases in the three-phase system. The value 1.732 represents the square root of 3, which is a factor used in three-phase power calculations. The power factor represents the relationship between real power and apparent power in the circuit. For purely resistive loads like heaters, the power factor is 1, indicating that all the power supplied is used effectively. To reiterate, the calculation provides the total wattage of the entire heater bank. If you need to determine the wattage of individual heaters, you will require additional information such as the number of heaters in the bank and how the total wattage is distributed among them. For conductor sizing, you need to know the full load amperage of the heater bank. You can determine this value using the total wattage that was calculated. The formula to find the amperage when you know the wattage in a three-phase circuit is amps equals watts divided by volts divided by 1.732. In this case, amps equals 2560 divided by 240 divided by 1.732, which equals 6.14 amps. Next, you would need to consult the National Electrical Code, or NEC, to determine the appropriate wire size. Table 310.15. B16 typically provides the ampacity of different wire gauges based on insulation type and temperature rating. When selecting a conductor, make sure that its ampacity is equal to or greater than 125% of the continuous load, as per NEC section 215.3 or 215.2, depending on the specific application. Continuous load is defined as a load where the maximum current is expected to continue for 3 hours or more. In this case, 6.14 amps times 1.25 equals 7.68 amps. Keep in mind this is a generalized example. Always consult the latest edition of the NEC and local electrical codes for accurate and compliant conductor sizing. The NEC provides tables for ampacity based on conductor material, insulation type, and installation conditions. Some common insulation types are THHN, THWN, and XHHW. Each has a different temperature rating, such as 75 degrees Celsius or 90 degrees Celsius. The higher the temperature rating, the more current the conductor can safely carry. The ambient temperature where the conductors are installed also affects their ampacity. Higher ambient temperatures reduce the conductor's ability to dissipate heat, lowering its ampacity. NEC Table 310.15. B2 provides correction factors for ampacity based on ambient temperature. If multiple current-carrying conductors are bundled together in a conduit or cable, their ampacity must be derated. This is because bundled conductors generate more heat than individually installed conductors. NEC Table 310.15. B3 provides adjustment factors for the number of current-carrying conductors in a raceway or cable. The termination temperature rating of the equipment the conductors are connected to is also important. NEC Section 110.14. C requires that conductors be selected and installed so that their temperature rating is not exceeded. The most common termination temperature ratings are 60 degrees Celsius and 75 degrees Celsius. After determining the corrected ampacity of the conductor and verifying it meets the termination requirements of the equipment, you must then determine the correct size overcurrent protection device. Overcurrent protection devices include circuit breakers and fuses. These devices protect the conductors from overload and short-circuit conditions. The overcurrent protection device must be sized to protect the conductor according to its ampacity. NEC Section 240.4. B provides rules for the overcurrent protection of conductors. Generally, the overcurrent protection device should not exceed the conductor's ampacity. However, there are exceptions for certain applications where the overcurrent protection device can be rounded up to the next standard size. You will also need to consider the voltage drop. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. NEC Section 215.2. 8.1 provides recommendations for voltage drop in branch circuits and feeders. For feeders, the voltage drop should not exceed 3%, and the total voltage drop to the farthest point should not exceed 5%. Voltage drop can be calculated using Ohm's law. The formula for voltage drop is voltage drop equals current times resistance. The resistance of the conductor can be obtained from NEC Chapter 9 Table 8. To reduce voltage drop, you can increase the conductor size or reduce the length of the conductor run. Remember to consult the latest edition of the NEC and local electrical codes to ensure accurate and compliant conductor sizing and overcurrent protection. Incorrect sizing can lead to overheating, fires, and equipment damage. In summary, to calculate the wattage of a three-phase heater bank, you must firstly calculate the line current. To calculate the line current, you will need to use the formula line current equals voltage line to line divided by resistance times the square root of 3. Secondly, you must determine the power factor. For purely resistive loads like heaters, the power factor is equal to 1. Thirdly, you must calculate the wattage using the formula wattage equals 1.732 times voltage line to line times line current times power factor. And finally, remember that this formula assumes a balanced three-phase load, and to determine the wattage of individual heaters, you would need to know the number of heaters and the wattage distribution among them. In order to determine conductor size and calculate the full load amperage of the heater bank, consult the NEC for ampacity based on conductor material, insulation type, and installation conditions. Apply correction factors for ambient temperature and the number of conductors in a raceway or cable. Verify the termination temperature rating of the equipment. Select an overcurrent protection device size to protect the conductor according to its ampacity, and calculate the voltage drop to ensure it meets the NEC recommendations. Always consult the latest edition of the NEC and local electrical codes to ensure accurate and compliant conductor sizing and overcurrent protection.